Is Zoom all set? Should be. Yeah, so we should get started.
Pretty silent, so
Yeah, perfect. So welcome everyone to the colloquium. It is my great pleasure to welcome Professor Robert Simcoe to deliver our colloquium today. Professor Simcoe comes to us from just down the street at MIT, where he is the Francis L. Friedman Professor of Physics, as well as the Director of the Kavli Institute for Astrophysics and Space Research. He got his bachelor's at Princeton and his PhD at Caltech before becoming a Pappalardo Fellow at MIT, and shortly thereafter joining the faculty in 2006. He's an expert in extragalactic observation and astronomical instrumentation, particularly in the infrared. So Professor Simcoe has received numerous awards and commendations and such over his career, but I want to highlight one specific rare distinction, which is that Rob was my academic advisor. And,
Rob, the highest of honor.
Exactly. And Rob was the one who suggested offhand, when I was in my junior year, that I reach out to Shep to work with the EHT as just a fun little summer internship. And for me, at least, the rest has been history.
Yeah.
So thank you for that, Rob.
And thank you, Rob.
I'm just really slugging albatross around their heads, you know. So it's an honor to have you here. So we still have a few slots open for dinner tonight, so please do sign up soon if you'd like to join. And otherwise, the floor is yours as you tell us about observational insights on supermassive black hole growth from JWST. Thank you, Rob.
Thanks for the nice introduction, Daniel. That's really funny. One of the joys of sticking around long enough in the field is seeing all these funny little connections that pop up. It's really a delight to get invited back by your former academic advisee. I'm going to talk about observations using JWST. As you mentioned, there's actually kind of an interesting angle to this talk for me in that to some extent, I'm not really an expert on black holes, even though I observe them a lot. Like I'm a real hardcore experimentalist, which makes this interesting territory. But I observe high redshift quasars, and I have for a long time. And that puts me into very close proximity with people who are experts on black holes. And so the way that I was going to structure this talk, in part because of that fact, and also in part because actually a lot of what I've been doing over the last few years is completely outside of this area. I've been working on this instrument, which is actually an optical instrument. This is an infrared instrument. This is the one that you were referring to, but this is the most recent one that we put on a month ago at Magellan. And this was the comet that was visible while we were doing it, so it's kind of fun. But because of this proximity to work that's been done with JWST, what I was going to do is use today to present kind of an overview, probably a slightly biased viewpoint, just based on the people that I come into contact with, and really my direct collaborators and work that we've done on high redshift black holes through GTO observations that we did with James Webb right after its launch. So because I'm an observer, it'll give you a sense. It gives me a little bit of an objective view in the sense that it's going to be an incomplete talk. Probably there'll be stuff that I don't necessarily refer to, but on the stuff that I do, you can kind of poke me about what seems more reliable and what doesn't from an experimentalist point of view, because I can talk openly about that. I don't have quite the same stakes in it. The folks that have done most of this work actually are shown here. So this is a collaboration that has spanned the globe. And it's got some folks that are centered at MIT here, Christina Eilers, Rohan Naidu, and Minghao Yu. And then Roman Bordaloy, who's now at NCSU, but had been at MIT. And then there's folks from Europe as well. So Yorat Methi, who's in Vienna now. We got Rory McKenzie and Daishi Kashino, who's in Japan. So this is a group that I spent a lot of time with on Zoom over the last several years, because we were working on a survey, which is called EIGER. So EIGER stands for, even though it's not readable here, it's emission line galaxies and intergalactic gas in the epoch of reionization. And what's significant about EIGER, so this is the same plot that I showed in the sort of title slide, but I just wanted to explain a little bit about what it is. And this screen is good enough that you can see all the calibration issues with it as well. But it sort of suggests that this is split up into a bunch of detectors that have been stitched together. But EIGER was a blind galaxy survey that is distinct from other surveys that have been done with JWST in that it was focused on fields that had known high redshift quasars in them. So there are 6 fields. Each of them had a very bright quasar. That's this one. So this is JO100 plus 28, which is an extremely bright quasar, the brightest quasar at redshift 6.3. And then we did wide field slitless spectroscopy. So I'll explain what that is in a minute, but this is the image of the field. And we already had spectra of the 6 quasars before we actually started this project. And so it was so bright that this is actually the ground-based spectrum of this quasar that has signal to noise larger than 100. And then this is actually a spectrum that came in from JWST in the rest frame optical. And that's something that we could not do from the ground, and we didn't have access to that until we had our slitless spectra from NIRCam. And I'll talk a little bit more about this spectrum and what we measured from it in a bit. But the point is that this is distinct from surveys like JADES and other things that you may have heard of with JWST, and that we were specifically targeting fields that had very known bright high redshift quasars. But we also got lots of other things for free. But the goal, when you take slitless spectra, the way that it works, well, I said that you could see how it was composed of a bunch of individual detectors and dithers. So the way that we strategize the observing is as follows. So this is taken with the NIRCam instrument, and we took images with NIRCam and we took spectra. So the images are in 3 different filters, and then the spectra are only with the long wavelength channel, and they are based at 3 microns. And you put a dispersive element into the beam, which without any slit in front of the disperser, so that you get a spectrum of every object in the field, but they all overlap on top of each other, and we have to disentangle that. And the way we did it, there's 2 channels. There's a red shows you where one of the detectors is, and then the blue shows you where the other is. But then we moved it around so that the 2 detectors are split on the sky, but then we moved the telescope around to sort of fill in those gaps, so that every single exposure actually was centered on the quasar here. So in each of these quasars, we had 20 hours of continuous integration. And then as you go out further from the quasar, the amount of integration that you get goes down in proportion to the amount of time that's spent. And so it's sort of like a wedding cake strategy for observations that's built into a single program. And then the way that you reduce the data, so here's an image showing a couple of high redshift galaxies. This is what they look like in our images. And then when you put the when you put the dispersing element in, which is a silicon prism, then it takes everything in the field and it disperses it. So wavelength is going increasing to the right in this view. What we see is this corresponds to this spectrum. This bright object corresponds to this spectrum. But then these 2 that are shown with the arrows here, they're sort of in the middle here. And then we do a filtering, we apply a filtering algorithm that takes out the foreground objects or things that have smooth spectra. And then we're looking for things that have very sharp emission lines. So it's basically what is it, a high pass filter, something like that. And then you end up with an image that's filtered that looks like this. And then when you see 3 dots that look like this, that are lined up for a single object, but they're lined up in the dispersion direction, then we can identify them based on the spacing between these to identify an oxygen 3 doublet and an associated H beta. So this sort of pattern of 3 shows you what the raw data look like well after it's been filtered. But you can see, like, there's no doubt that that's what these things are, right? So at first we were worried that they would be really weak detections. You can actually see them in the raw data here. So this is what this is the oxygen 3 doublet and H betas over here, but it comes out after you filter it.
What's the signal to noise?
For these,
Yeah.
for something like this oxygen 3, the signal to noise might be 20 to 30 in many of these cases, but it varies, right? There's always something that's your weakest. But for the majority of these, the emission lines were extremely strong. We were very surprised when we first did that. We got these, so they opened up JWST for observations in July, I think it was July 4th. And we had these at the end of July. And nobody expected the oxygen 3 lines to be this bright. So we expected to find a few objects per field, and we found several hundred instead. And that has to do with the way that the ionization works in these galaxies. They tend to sit at the particular set of metallicity and ionization conditions that give you a peak in oxygen 3. So the universe was kind of kind to us in that way. And the telescope was better than anybody thought it was going to be. Yeah.
So because of this filtering, you're automatically removing the continuum. Right?
That's correct. Yeah, so we go back and we can extract the continuum, but we filter it for object detection. So it's basically allows you to do pattern recognition, and it removes all the foreground stuff that, for the most part, has smooth continuum. So stars and galaxies, if you're looking at their continuum light. It's actually much harder to go back and study some of those things at lower redshift with the slitless prism. With other instruments, you can do it very effectively. So I guess what I should say is that so we're selecting based on oxygen 3 and H beta, so we don't have to do photometric selection, and we don't have to put slits on anything, which is nice because you get a spectrum of everything in the field. And it's a different kind of selection, but it's fairly complete and well defined. Once you put slits on things, it's a lot of work to figure out what your window function is. But because there's no slit, it also means that you're not going quite as deep. And so you might not be quite as sensitive as you would be with some other instruments like the NIRSpec MSA. However, there's still plenty of objects. And in fact, you know, it's deep enough to do lots of interesting science. And we figured out, well, we did population synthesis fits to all of these things. It's not, you wouldn't want to use our survey to find photometric redshifts because we only have 3 filters. But we measure 3 emission line fluxes, 2 oxygen 3 lines and an H beta. And then we also measure 3 photometric bands. And that actually allows you to find pretty good stellar masses, ages, and sizes for these galaxies. And so these things have about 10 to the 8th solar masses of stars. They're similar in size on average to the Magellanic Clouds. They're much more like those than they're actually more like the SMC than they are like the Milky Way. And you very much have to account for emission lines when doing these photometric fits because the emission lines actually dominate a lot of the flux. They're quite young, which is good because the universe is only about 1 billion years old. But the other thing that I would have you keep in mind is that the virial radii of these things are quite small because they're such small objects. We're used to the virial radius of a galaxy being, you know, hundreds of kiloparsecs, but these are like 10 or 20. So they're quite small, and there's lots of them. So that's the survey that sort of connected me to JWST, and I'm going to sort of fan out in a couple of different directions. Because this survey was used to do, you know, to address multiple science questions. But it also connected me with people that were working on other surveys that sort of influenced the way that I think about black hole growth in the early universe, which is where I'm kind of heading with all of this. I just started with the observational program because I'm an observer. The main science topics that we focused on were reionization using galaxies in the laminaire forest from the spectra that we have of the quasars. My particular interest is in early heavy element pollution. As I said, I'm not really an expert in quasars, which makes this interesting to talk about. I really am interested in the stuff in front of quasars. However, I've been working very closely with folks who did study quasar physics using the rest optical spectra. Also making early detections of their host galaxies, studying clustering in the environment of these early objects. And then we found some interesting things because we were taking a spectrum of every object in the field. There were some surprises that came up. And this is just saying what I mentioned earlier. These ideas that I'm talking about today that started with this program kind of influenced other thinking that happened. And as I said, you can poke at me about which ones I think are more reliable. And I'll try to, as I talk, I'll try to remember to sort of say what I think are the most trustworthy results and which ones you should be skeptical of. But if I forget, just ask. Okay, so I've showed a bunch of images, but actually the thing that's interesting is the redshifts, because we get these for every single object, allows you to basically rotate this and then separate everything in the depth dimension. And so this is kind of a figure that summarizes what we get. It's weird looking at it from this angle. I think it changes the perspective a little. So it basically sorts it so that you have in each of these 6 sight lines, you imagine in the middle is a quasar. It's not at the back, the way we usually think of for circumgalactic medium. So we have a redshift 6.3 quasar in a galaxy survey that goes from redshift 5.3 to 6.9. So these, there's a reason that these are mostly 6.3 and not higher. One is that we had to submit our targets way before JWST flew because we're a GTO program and not a GO. But the other is that for doing certain kinds of analysis, it's actually the lower redshift quasars are brighter. And also, when you get up to redshift 7, everything just has damping wings and there's no dynamic range in the absorption line signatures. So it's actually advantageous to do this at slightly lower redshift. But so here's your quasar that's shown with the yellow dot. And because we have a spectrum from the ground of the rest ultraviolet, we can measure what the transmission of the IGM, or the intergalactic medium, looks like, and that's shown with this purple curve. So you see that there's fluctuating transmission, then it goes to zero, and that's because the IGM is mostly neutral. Except occasionally we see, so the green dots here are oxygen-3 emitters, with the circle size being proportional to the virial radius of that galaxy. And you see that sometimes if there's a set of galaxies that's near the quasar sightline shown in red, then you see a little bump in the transmission of the IGM, as we would expect to see. That's a reionization signature. But the other thing that's interesting is not only can we look at foreground galaxy and absorber associations, but we're also interested in clustering at the quasar's redshift. So all these green dots that you see around the quasar, that's hierarchical clustering of smaller galaxies around the halo that's hosting the quasar. And then there's, in addition, there's galaxies that are behind the quasar. So you see that they sort of thin out in density, but I'm going to come back to this, that there's a little cluster of galaxies in this one field that's a redshift 6.8. So it's significantly behind the quasar, which might seem initially uninteresting, but there's an interesting application we can do. So the data set includes that. We've got these ground-based quasar spectra. Now we have a rest frame optical spectrum of the quasar with unreal signal-to-noise ratio because we've been going for 20 hours to get these faint objects. And we get the bright quasar for free. And then we get a spectrum of every other object in the field.
Rob,
So, yes,
those background green fellows,
yes.
they seem to be concentrated around the quasar. Is it because you look deeper in the center, or is that lensing bias or something?
So you should think of this as like a narrow cylinder, right? So because that's set by the field of view of the
Yeah,
telescope.
but what is
right?
the field of view in this diagram? Is it the whole square, or is
So it's about the size of, I wish I could draw on this, but it's sort of a diagonal in this field of view. Actually, sorry?
You can annotate it on the slide.
Oh, I can. No, if I have faith in my ability to do that. Let's see what happens. Oh, there it is. I have a pencil now. Okay. But I have no.
Breaking new ground.
All
it's
right.
time for the BHI?
That's how you, when you invite an experimentalist. The field of view would look about like that.
Okay, and you say the green dots are actually filling that field of view uniformly, or are they concentrated?
Fairly so. Actually, there's a better way I can answer this by zipping ahead in my presentation a little bit. Because I've got another view of this that I'll come back to. Apologies here. So, it hasn't gone away.
There was an eraser symbol if you go back
Yeah.
to that other menu.
Well, it's easy. I'll let you enjoy that.
It's our comfort rectangle.
So this is actually, if you were to look down the barrel of this, you would see something that looks like that.
Okay,
Does that make sense? And answer your question, sort of. So they don't uniformly fill the field. But one of the things that people often don't appreciate is that how very long and thin these surveys are, right? It's the co-moving
The
distance in the
pencil beam
line of sight
surveys.
direction is always that way, right? Sorry?
The pencil beam surveys.
Yeah, that's exactly right.
But to Ramesh's point, these aren't lens.
Correct. Yeah, these are just regular old quasars.
no, not the quasar, I was thinking the background.
Yeah.
Galaxy
yeah.
might have
I'm
been
talking about
lens.
those oxygen-free.
Yeah.
Sources.
Yeah, it's not obvious that these things are lensed. I don't know how to get rid of that thing, so I'm just gonna.
If you go to the lower.
Yeah, if you go back to the same annotation menu that you were
There's
on
an
before,
eraser.
you can also just click the trash can.
There it is.
There you go.
Go back to this. All right. And now back to our regularly scheduled programming. I hope people on Zoom can actually see what's happening. I have no idea. Okay, that's our data. So let me make a little side quest. As I said, my own science is focused on the circumgalactic medium of these foreground things. So I'm going to spend a slide and a half talking about this just because. And there's actually very little published about this, any of circumgalactic medium science so far, because it just takes longer to do this stuff because you've got to really do a careful analysis of the quasar spectrum and the galaxies. But something I'll just leave here for you is that we actually do see a significant number of associations where there's foreground galaxies and we can see metal absorption from the circumgalactic medium of these galaxies. But remember what I told you earlier, that these galaxies are 10 to the 8th solar masses of stars. So when we often, people have a mind's eye view of the CGM that is informed by surveys like COS halos. But these galaxies are 250 times smaller than the COS halos that are like L star at redshift 0 and have virial radii of 200 kiloparsecs. And so these things, you see associations with the metal lines, and here's what they look like. So I've circled galaxies. If they're the quasar, these the circles represent galaxies, and if they're filled, that means that we found a metal line absorption system at coincident redshift within 1,000 kilometers per second. If they're open, it means that we haven't found a metal line system, and so we find it about half the time. But the diameter of that, or the radius of that circle, is equal to R200, so the virial radius of that galaxy. And the point I just want to make is, in almost every one of these cases, we see association with metals, but those metals are not inside the galaxy in the same way that they are at redshift 0 for things that have been observed with COS. And so it's kind of a new way of thinking about this. And there's a whole talk that I could give about, like, are there lower mass galaxies that are nearby that we don't see? Or is it the case that these things just are not capable of binding the metals that they produce in supernovae, and that you're seeing stuff that has flown out past the virial radius and is actually truly in intergalactic space? And that's what we're trying to get to the bottom of. Or is it just the case that, you're randomly seeing associations?
That maybe unbound gas is what you think? Okay.
I think there's a pretty good chance. That's my working hypothesis as to what it is. We're pretty sure that it's not just a chance coincidence. So we can actually make projected cross correlation functions between carbon-4 absorption systems and galaxies. And you can see that this has a significant amplitude at small transverse separations, but it has non-zero. So this is, a cross correlation of 10 times the random out at 100 kiloparsecs, which would not surprise you at redshift 0, except for the fact that the average, so this is the virial radii of these same galaxies, and the median is 17 kiloparsecs. And so circumgalactic, what does that mean? I don't know. But I want to sort of encourage people to start thinking about this in a new way. There was some enrichment that happened outside the galaxies earlier. But these aren't black holes, so we're moving on. So let's talk about early black hole masses. So I'm basically going to list off a bunch of things that have changed about the way I think about early black holes based on observations that we've done. And it's not so much, so there's a lot of interesting literature that's emerging about people finding black holes and quasars at very early times, at redshifts way beyond what, we're only going to 6.9 here, which sounds like a crazy thing to have said 2 years ago, but that's where we are. I'm not going to focus so much on those very early ones, instead sort of focus on the physics of black holes in the redshifts that we can probe. So, so here's something that might not really be mind-blowing, but I'm just going to say it because it was something that we had to test. So for a long time, it was the case that if you wanted to measure black hole masses at redshifts beyond a certain value, I can't remember exactly where it is, but all of this stuff is tied to reverberation mapping measurements that are made at redshift 0 that are usually based off of H beta. But once H beta redshifts out of your window, you need to use another rest frame UV line. And typically it was magnesium 2. And people have been using magnesium 2 measurements. So this is the quasar spectrum I showed earlier. There's the magnesium 2 line, which is not much to speak of. But you would fit the velocity width of this line. And then you would correlate the magnesium 2 line width with the H beta line width, and then correlate the H beta with the reverberation mapping. So there was like a ladder that you had to follow. And one of the nice things with JWST is nobody actually knew what the H beta line widths were going to be out there. But with our first spectrum, we could measure. So here's H beta in our NIRCam slitless prism spectrum at very high signal to noise, as I said before. Excuse me. And so you can fit multiple components to this and actually fit what the line width is, removing one rung from the ladder that's used to infer those black hole masses. And so here's the formula that's based off the reverberation mapping measurements. And so the black hole masses are 10 to the 7. The full width half maxes of these, what we found is they're still in H beta, several thousand kilometers per second. They're not small for these bright quasars. And then the quasars are very bright. So if they're small, or if they're broad and they're bright, you're going to get a large mass. The way I think about this as an observer, again, is not to say the black hole masses are large, but is really that there's no systematic change in the H beta velocity widths or the for bright quasars as you go to very high redshift. And if you believe that correlates with black hole mass, then great. It probably does. I guess the only remaining uncertainty that's left in this whole ladder is do the reverberation masses. Does this relationship still hold at high redshift? We don't know that. I think eventually what we're going to have to do is wait for these things to vary, and then we will we'll take reverberation measurements at high redshift. It's just that you have to be very patient because you've got a factor of 1 + c that's working against you in time. But we are starting to find quasars that vary at those very early times. So yes, there's no evidence that something is changing based on the JWST measurements. So that's just one object, but here's several objects where the same was measured by Meng Yu. And then here's another way of looking at it, that these are the H beta black hole masses, and these are the magnesium-2 black hole masses. And then the 1-to-1 line is shown here. These points are lower redshift, and then the red points are the ones from our survey. And then the orange ones are from another survey called Aspire, which is a similar strategy. It's just they observe more quasars. It's somewhat less depth, but it's very good for the same measurement. And so Jin Yang had done that work. And so you can see that, there's a lot of scatter, but they more or less fall at the 1-to-1 line.
I have a naive question. Do you see a trace of the jet in what you observed? Is there a jet?
So I assume that there probably is, but we don't see any observational trace of it. There's a couple where our group has seen what looks like they might be filamentary structure in oxygen-3 that's extending outwards in the slitless prism spectrum. But we argued a lot about whether that's real or not. There hasn't been an unequivocal detection of that. And also the oxygen-3 might not be a jet. It's the stuff that we see looks sort of narrow and collimated.
Yeah.
So it's either a jet that's going out or a filament that's coming in. But that's the closest I could say to finding a trace. Okay, so the next thing, again, we're not the only group that looked at this, but it sort of looks like black hole growth inside of early galaxies. I say the chicken comes before the egg. That's if you think that the black hole's the chicken. I've spent a while trying to figure out which is which here. But that's the way this question goes. So this comes from looking at the host galaxies and their stellar populations. So another way of stating this is that it seems that the black holes may have grown faster than their host stellar populations. And so this is the sort of way that I was convinced that this might be true. So we started looking at the NIRCam images to see if we could subtract a model of the PSF and still detect a host galaxy and residual. And so this is one of those models. In fact, we didn't subtract the PSF and then look for the residual. What we actually did was fit a forward model that had all the PSF of the quasar plus everything else. And then you can subtract off that component of the model so that you actually have correct error bars. But the point is that, so this is the raw image that comes off. And the model for the host that comes out of that is shown in this column here. These are the 3 different filters. This is the same object. So going across is one filter. So you have the raw image, the host model, the PSF subtracted model, and then the residual map when all is done. And what you can see here, so there's obviously residuals from the PSF, but you can see that there's something down here to the lower right. And it looks like there's extended emission that goes beyond just the location of the PSF proper. And so we introduced some formal criteria for how much the chi-squared has to improve by adding the host. And there's sort of a goodness of fit test. And then this is actually a map of basically the signal to noise. So these are signal to noise of residual flux that doesn't come from the quasar. And you can see that there's clearly in the reddest filter, there's a signature that you see here. And actually you see emission lines from this in oxygen-3 as well. So we have reason to believe it's at the same redshift and not just something that's in the foreground. So this is one where we're pretty sure we detected something. Here's another one where we're pretty sure we detected something, but it's interesting that this is offset. It's not, the quasar is not in the middle of the galaxy in this particular case. So it may be some byproduct of a merger. This is our highest redshift case. This is at redshift 7. And then this the ellipse here shows you the location of the model galaxy. And then there's other ones where we don't detect anything. So here's one that's actually a very bright and famous quasar. And when we fit the model, there was no indication that adding a galaxy improved the model at all. So sort of in half the cases we could detect a galaxy, and half we could not. And you can argue about even the cases that I showed where we said we detected a galaxy. But remember, the scientifically interesting thing is that for the size of the black holes that we measure, we should have seen more galaxy, right? If you don't believe those detections are real, that makes the problem worse, not better. Okay. And so one way of looking at this, you've probably seen plots that look like this. We're not the only ones who have done this, I think. Many other groups have done it. And are finding sort of similar results. So these are showing at low redshift, the relationship between the stellar mass that you get from fitting photometry to the PSF subtracted image. And then this is the mass of black hole. So another way of thinking about this, an observer's standpoint would be, this is the F356W magnitude, and then this is the velocity width of H beta, right? And so if you don't believe, that these mappings, at least just think about what is the actual observable that's changing. And really what it is for a given velocity width of H beta, you're seeing less photometric light. And so the points that we had are shown in red here. I think that at the time this was published, there were several other groups that had made similar measurements. But the point is that they tend to lie either above or to the left of the relationship that you would have at redshift 0, which is shown in the gray here.
What is the surface brightness limit of the residuals you have?
The
the
surface
stellar
brightness
component.
limit.
How low a blob are you able, stellar blob are you able to pick up in there?
That's a good question. I don't know in terms of magnitudes per square arc second, but I know that these things, I think their magnitudes are like 27 or so, the integrated magnitudes. Yeah.
All right, what is H beta?
H beta is the Balmer, so H alpha would be the n equals 3 to 2, right? Balmer line, and then H beta would be the next one in the series.
I mean, I was wondering whether what you're really seeing is one star forming region, but you're missing out all the other extended lower surface brightness stuff, which is the stellar component as well.
Yes, I see what you're saying. So it's not the case that the surface brightness is dominated by the nebular emission. But the once you get outside the PSF, we're just the same as any other object. Well, I mean, we can see things in our survey that are down here, right? So as I said, our typical galaxy is at 10 to the 8th in stellar mass. But those would be right on top of the quasar. And so we're seeing the outer regions of those, but we're still already seeing stellar masses of more like 10 to the 10. So these are brighter than our typical galaxies.
The question is how quickly you get to the background outside your postage stand.
Yes,
Right.
yeah.
That's
And that's a question that I can't answer. It's one that I don't necessarily worry invalidates this, but it's a good point. For reference, if you actually do the math out, this says that the black hole masses are 10 to 15% of the mass of the host. Whereas at low redshift, you would expect it to be 0.3% of the mass of the bulge, or 0.03 mass or percent of the total mass of the star. So it's much higher than it would be at low redshift. But the errors are large. However, the point is that we should have seen more starlight and not less. And that's usually the easier problem to have faith in. You do have to worry a little bit. We're only choosing very bright quasars around which to do this because these are the first ones that were observed with JWST. And so there's a question, like if you only observe very bright high redshift quasars, and then you sample randomly from the distribution of quasar luminosities and randomly from the distribution of host galaxies, are you likely to present some biased sample that would invalidate this result? And this is the thing that worries me the most, actually. And we're just going to have to wait longer until JWST observes more objects. So yes, you can. So we did this test just using a Monte Carlo draw. And you can see that if this is the low redshift data trend, this does tend to move you in the same direction that we're seeing here. It doesn't move as far as the points that we've seen, but just the fact that the trend moves in the same direction, I think should give one pause. So I think it's very interesting, but I would wait and watch to see how this develops. Once JWST has been around long enough that people are doing samples that are constructed more uniformly and not cherry picked, as happens in the beginning of missions like this, it's more confident. Okay, here's the next topic that I wanted to discuss about things I've learned. So it's that these bright quasars, remember, we're looking at the biggest and brightest quasars at this redshift. These are, at least our survey was. These live in dark matter halos that have about 10 to the 12 solar masses of dark matter. Although there's exceptions and there's things that are high and low. But the sort of point 4 is that the clustering implies that there's a very low duty cycle that these quasars are visible is optically in UV bright sources. I'll go through the logic and try to explain how it is that clustering tells us what the duty cycle is. It's not immediately obvious, or it wasn't to me, how this works. So here's just let me just show you some raw data for 4 different fields to give you a sense of what we were expecting and what we saw. So what I'm showing here at the top is the image for each of those fields. The arrow points to where the quasar is. That was the center of the survey. Those are the known quasars at redshift sort of 6 to 6.5. What is the 7? And then down below, this is the ground-based spectrum of that same quasar. And then the dots here show the locations where we have detected galaxies using JWST. And so the distance that the dot is vertically tells you what its projected distance is from the quasar sightline. So in the direction along the screen here. And the circles here show you the locations of galaxies that are at the same redshift as the quasar, or very close to it. So they're within this gray band. And so you see at this location that there's only 2 galaxies in addition to the quasar, this one and this one, that are at the same redshift. And actually, this is what you would expect if these quasars were sitting in a random field, that we'd have about two objects per field that were coincident in redshift with the quasar based on our prior assumptions about clustering. So here's another one, which shows you somewhat different results. So again, here's the location of the quasar, but you see where our expectation value for the number of galaxies clustered was 2. This one had significantly more. And so you see again in the gray band here, all of these ones here are the ones that are circled in the plot. And the usual assumption is that when you see a larger clustering like this, it means you're in a more biased region of the universe, and therefore that the quasar would be sitting in a dark matter halo of higher mass. So let me show you 2 more fields. Does that all make sense? So far, so good. Okay. So here's 2 more fields. So what you see is this one was a little weird. This is our first field, and we were very worried that it looks like there's a huge overdensity, but they're all on this side of the chip. So we were worried that maybe one half of the instrument was more sensitive than the other, and so we flipped it around and like played games like that. And actually, that's really where they are. And so the quasar is actually off to the side of whatever this overdensity is. And then this one is just in a gigantic overdensity. There's a large number of objects at the same redshift. Again, you see them all piled up here at the location of the quasar. You might ask how we know what the redshift of the quasar is, but we actually have all our redshifts with the carbon-2 fine structure line that gives us a very accurate estimate of what the systemic redshift of the quasar. Yes.
Are these clusters at all like evidence for like inflation, galactic expansion, like in relation to what could be AO?
So I think this has more to do with the the degree of, well, it's not so much BAO as dark matter clustering is the way that we've interpreted this. That if you imagine that the brightest quasars, if you have an ansatz that says the brightest quasars sit in the most massive dark matter halos, because the brightest ones usually correspond to the most massive, black holes, and the most massive black holes are the ones that started growing the earliest. So there's that chain of logic. And then the biggest galaxy should sit in the biggest overdensities of dark matter. So it really has more to tell you about the properties of the dark matter that gave rise to these very early overdensities of galaxies. And that by measuring the number of galaxies that are clustered around it, it tells us how big is the halo that's hosting this in a sort of, it's a very model dependent way, but the model depends only on the flavor of dark matter that you choose. And the baryon acoustic oscillations are something different. Like, so they would tell you about clustering that's at much larger scales, that if you see another peak that is out at much larger distances. But this is, instead of the sort of term that's off, like the 2 halo term, this would be like, we're looking at 1 halo clustering. That's not exactly the right way of describing it, I think, but maybe that's how I think about it. Okay, so there's that. So one way of looking at this is if you count up the number of smaller clustered galaxies, and then look in simulations that are dark matter only that say, how big is a halo that has this many smaller objects clustered around it? What you would find is that it has a mass of about 10 to the 12 solar masses. So this is a different way of looking at it. So this is showing the clustering amplitude. So this 1 plus delta is the overdensity or the excess probability that you see galaxies in the same volume relative to a random field. And so for one field here, it basically is the same as a random place in the universe. That was that first field that I showed you. But the last field I showed you has 100 times more galaxies than you would expect from a random place in the universe. And you can see it goes, all in between. But when you compare that to dark matter simulations, you can turn this into a clustering amplitude. So this is the volume average projected correlation function. And you see that at small transverse separations, this is also another measure of the excess probability of seeing another galaxy near where you are. And you see that it's very large at small transverse separation, and then it goes down. But then you compare to simulations that have dark matter halos of different sizes. And so what you see here, this is if the quasars were housed in halos that had 10 to the 11, 10 to the 12, 12.4, 12.9, 13. So as the halos get more massive, their clustering extends over larger distances. And by measuring this distance, we can estimate the size of the average halo where one of these black holes is growing. And we find that it's about 12.4 in the log. Remember, this is an ensemble average. It's not any single object, but it gives you some sense of this. But what it means, yeah, it's like the size of the Milky Way today, but except this is at redshift.
So does this mean that the dark matter fraction or the baryon fraction varies a lot? There's a lot of variation from source to source.
I think so. It probably also means that there's this idea that when you see a quasar, it always represents the center of the most massive galaxy that sits in the center of a big dark matter halo. It's probably a lot more random than that, right? That what actually happens to produce a quasar may have as much to do with microphysics. But on average, if it was only microphysics, then you would never see this, right? I think what happens is that there's just more galaxies here, and you increase the odds that one of them happens to be in the UV bright phase. And we'll talk about the duty cycle of that UV bright phase now, and why there's lots of evidence for obscured black hole growth. So I said I would mention duty cycle and why this has anything to say about what fraction of the time a black hole is shining in the UV. So the way that you can do this calculation is as follows. So we know from counting luminosity functions how many quasars there are in the universe, roughly at that point in time. And it's about 1 per 4 cubic gigaparsec at redshift 3 and change. But if you say how many halos are there that have a mass larger than 10 to the 12.4, then that should be 53 per cubic gigaparsec, plus or minus some. And that comes from counting these n-body simulations. And so then you could just take the ratio of those two, and it tells you which fraction of galaxies that we think host quasars are actually presenting as a quasar at this moment in time. And the answer to that is just the ratio of those two. And within errors, it's sort of like 1% with sort of logarithmic error bar of sort of 1 dex.
Wait, sorry, is the halo density in the line of sight the -1 exponent?
I think it's a typo.
Sorry, so the halo number density. This is
Why isn't
per
it gigaparsec
moving
cube?
gigaparsec to -1.
Oh, yes, sorry, that should be a
Oh,
minus
sorry,
3.
so it's not line of sight.
Yeah, it's a
Sure.
LaTeX error.
No,
Thank you for catching
no,
that.
no.
Yeah, these should both be per gigaparsec cubed.
Right.
But the point is that there's only 1 in 100 or 1 in 1,000 quasars, or well, 1 in 100 to 1 in 1,000 black holes, which we assume are at the center of these galaxies, are actually shining in a way that allows us to select them using UV light as a quasar. And what it also means is for every quasar we see, there's probably between 100 and 1,000 other accreting black holes that we don't see, and we have no mechanism for detecting at this point. So what's happened? So another way of looking at this, you've seen this problem over here probably. If the universe is just less than a giga-year old, then we have a quasar that has 10 to the 9 solar masses, and it's accreting at the Eddington rate for its entire history. You still have a problem getting down to a stellar mass seed. You have to have some other seed that's either a direct collapse or some star cluster or POP3, some big remnant. But that assumes that you have all this time. But if it's only accreting, if you imagine that this is the fraction of time that you're accreting, then this little bar here tells you what fraction, what amount of time you have to accrete that. And so you can sort of see that there's a problem unless you invoke something else. Yes.
You also told us that we are looking at the bright end
Yes.
of the complete distribution.
Mhm.
Would you get back the factor of 100 if you just said, okay, now let me expand this to the whole potential distribution, including the ones that are fainter? That's going to give a correction. Is it as much as 100?
I think that's probably right. But I mean, that's
So they're
the
there,
avenue that we're searching. We think they're there.
they're there, and they're just look too faint for us to pick
Yeah.
them.
From an observer standpoint, the question is like, if they're out there, let's go get them, right?
Right.
And I assume that that's true. I'm going to talk about one candidate for how you might get back some of this number. But I think there's other ways that you might search for them as well.
I mean,
But that would mean the duty cycle is one.
The duty cycle is one if you can find enough of them.
Okay.
Using these other techniques.
Right, but if you look at the lower redshift luminosity functions of quasars, it's quite steep in the faint end, right?
Yep.
So you could easily get that factor of 100
Mhm.
at lower redshift.
But it's
So we
also true
assume
that
the shape stays the same.
Assuming, yeah, right,
Assuming,
of course, if
yeah.
we say the whole thing is shifted.
Yeah.
That's a different story.
It's also true that at lower redshift, the Sultan argument says that we've already found enough quasars. If you give yourself a current Hubble time to explain the existence of one black hole in the middle of every galaxy, more or less, right? And that this point here is that at high redshift, that doesn't work so well. And I think that's just because more quasars are presenting, or more black holes are presenting as UV bright quasars at lower redshift, I think. But that's my interpretation of it, but we've got to go find these things.
Mhm.
So I would say either the accretion is highly Eddington, super Eddington, or a lot of black hole growth is obscured in the UV. I think probably both of these are true. Okay, so another topic here that's interesting, if you want to know what the radiation looks like coming out of these things. So we think it's almost certainly episodic and non-isotropic. So let me explain why we think that's true. So the episodic argument kind of predates JWST. But if you look at the spectrum of the quasar, which is basically inverted in this pink line, pardon me. So it's well known that above redshift 6, you see this Gunn-Peterson trough where there's zero transmission in the intergalactic medium because a larger fraction of the hydrogen is neutral. At redshift 6, it's not all neutral yet, but it's enough to make this on resonance absorption saturate. But it goes non-zero as you get close to the quasar. And the assumption is always that this is caused by the quasar ionizing its immediate surroundings, similar to what a Stromgren sphere would do, but it's not exactly analogous. And that the size of the ionized region, so that the fact that it's ionized is what increases the transmission here, right? Because ionized intergalactic gas transmits UV photons and neutral intergalactic gas doesn't. So we imagine that there's an ionized region or a bubble of some sort around the quasar, and it's expanding with time. So once the quasar turns on, there's no ionized bubble, and over time it grows outwards. And you can calculate what that looks like in simulations, and you can compare it with the sizes of these little proximity zones, right? So here's a quasar spectrum, and this is the width of its zone where it goes from where you see all the light from the quasar to where you see none. And the size of this is basically a measure of the size of that bubble. And when you run this in simulations, what you see is you turn on a quasar and the size of the bubble, which we call the proximity zone, goes up and up and up until it saturates. And so it takes about 10,000 to 100,000 years, and it saturates once the number of photons that the quasar is producing are equal to the number of recombinations of hydrogen inside that bubble. And then it goes up later on when you reionize helium-2 around it. But the point of this is that for this particular object, you measure the size of its proximity zone, which is shown in this horizontal band, And that gives you a constraint on how long it has been shining, right? And the answer here is that it peaks around 10 to the 4 to 10 to the 4.5 years, with some long tail, that because of the fact that this distribution flattens out once you saturate. Okay, so that's all good. But the point is, once the quasar turns on, it's actually pretty fast. It only takes 10,000 years after it turns on to saturate. And if you turn off the quasar, it's also the case that it recombines in 10,000 years. So it's actually a pretty sensitive chronometer. And we found a large number of these quasars that have lifetimes of 10 to the 4 years. And so we don't really think that they've only been accreting for 10 to the 4 years. We think it's much more likely that they're turning on and off all the time. That means that either there's some fraction of the time that it's accreting, which sort of compounds that problem about the timescales for black hole growth again, or that the time that it's not shining in UV bright phase, it's just obscured. And it's still growing. It's just that we can't see it.
So are these the same black holes that were like 30%, with the 30% of the stellar mass?
Yeah, I guess they would be.
Yeah. How did they get, if they're episodic, how did they grow so fast? How did they get to be such a big fraction?
I think probably what's happening is that they're still growing all of that time. It's just that we don't see it. So the underlying argument here is that when it's UV bright, it's growing, and when it's not UV bright, it's not growing. But the black holes that we see are all UV bright because we select them that way. Okay. So just to this point of looking at the ionized region around the quasar, I mentioned before that I was going to talk about these galaxies that are behind the quasar that would otherwise be uninteresting for this particular kind of science, except for the fact that every once in a while you see a little cluster of galaxies just randomly behind the quasar. And what's kind of fun about these is that every single one of those is shining back towards the Earth, right? And so if they're in the same field as this quasar, the light from this object is going to traverse through the ionized bubble en route from the galaxy to the Earth. And if it goes through a region that's ionized, then the IGM should not transmit photons for redshifts that are behind the quasar, and it should not transmit photons in front of the quasar either. But there may be the case, it may be the case that when it goes through the ionized bubble, there's a portion of the spectrum where it allows transmission of photons. And JWST is actually sense enough to detect this in principle. And so you can actually look for what we call transverse proximity effect, or the transverse ionization of intergalactic gas. So if you imagine that those background galaxies are over here, and now we're shining light in this direction, and then the star is the location of the quasar. Once you turn on the quasar, it's going to actually ionize. So if we call the blue regions here neutral and the yellow ones ionized, this actually produces a parabola because first the light has to get from the quasar to ionize it and then got to get through. And so there's a surface that once you turn on the quasar, instead of expanding as a sphere from the perspective of the observer, it sort of expands outwards as a parabola and then goes back. But it's also the case that we don't know whether quasars are shining isotropically or whether they're obscured in some directions and shining UV bright in others. And if you look at what the predicted transmission is along these three sight lines, you get a slightly different signature. If you have a young quasar that just turned on, it looks like this. And this whole area behind it looks neutral, so that you only see transmission between, looks like it's in front of the quasar. Whereas if it's older, but has a non-isotropic radiation field, then you'll see transmission before and behind the quasar, but there will be regions where there's no transmission. And the regions of no transmission correspond to these segments, here, here, and here. And the ionized segments are where the transmission occurs.
When you say isotropic, is that shorthand for jet, or is it something else?
No, shorthand for like if you have some, like a torus or some obscuring, dust. We don't know what, but just something that makes it not shine uniformly in all directions. So those are, so I promise not to say anything more about this, other than that.
Oh, wait, say more.
So
have you seen this?
Yes, we've seen it. And it's more like this. Moving on.
But you've seen it, but are those the actual?
Those are not the actual spectrum. I showed you a simulated sightlines that we used to assess whether it was possible to do this experiment or not. And now the experiment
I'm
is
saying, why are you not showing us that cool stuff?
because it's we're pretty sure that it's correct, but it represents an extreme data reduction challenge to do this. I said there are some results I trust more than others, but I trust them for different reasons. And like I said, I distrust some of the, but at least I'm cautious about this mass of the black hole versus mass of the stellar population because there are selection effects with only doing bright quasars. In this particular result, I think it's pretty solid, but it is the hardest data reduction challenge I've seen with JWST. So until we are sure that it's rock solid, I want to withhold judgment on it, but I'll just point it out by way of teasing it. Okay, now to Ramesh's question. What about those other 9, who are the 99%? Not picked up by this conventional UV selection. So here's one candidate. So one of the things that we found with our slitless GRISM spectra in IGER in a companion survey called Fresco is that there were sources that had broad Balmer lines, broad H beta, that we were not expecting. And this is what these objects look like. We saw that they all had a very compact morphology and they had somewhat unusual colors. But you can see that each of these things has quite broad. So this is just the broad H beta is shown here in these in the 2D spectrum, and then this is the 1D extraction of it. And these are not objects that would have been selected as quasars, but they don't look like galaxies either, particularly in the red filters. And so Jorrit Mathy had led this, but at the same time, there were other groups, including JADES, who had found lots of these things. And we actually, so the paper that Jorrit wrote named these things the little red dots. What people don't know, they're not called little, but we didn't start calling them that because of their morphology. It was because Rohan Naidu is in our group too, and he was from Singapore. And Singapore is often called the little red dot because it's a little country, and they have all these kids books. They're like very proud about the little red dots, and there's little cartoons that are like that. And we thought they were very cute. And so we started calling them these things, and then it made its way into the paper, and somehow that name is stuck. So there's lots to say about these, and I'm going to focus on one particular angle of them. And I would say that what most people have noticed about these is their very distinctive spectral energy distribution. So this is a stack of 400 little red dots. And the interesting thing is really this central, like all the discovery space has been in here. So JWST has found them rising to the red, but then once you go blueward of the Balmer break at roughly 4,000 angstroms, then they look blue. And what people are saying is that this is some combination of a star-forming galaxy in the blue and then something else in the red. And that something else, we don't know what it is. But there's some speculation that the red side may be some signature of an obscured AGN that has a smaller mass than the gigantic ones that we were studying with the IGER quasars. So these are exactly the kind of things we were talking about. And then there's a possibility that these things recover in the X-ray. If it's just obscuration, you might look for them there, but we haven't seen a convincing detection of X-ray yet. I know that Fabio's worked on this a little bit, and there's a question of whether this is pure obscuration or there's some accretion physics and geometry that could explain this. I won't talk about this too much. I mean, being up the street, we're big proponents of the AXIS mission, and I would really love to be able to observe these things in much greater depth. And I think AXIS is getting really deep X-ray spectra will, I think, in the same way that JWST has opened up a sort of parameter space for studying high redshift black holes, I think the X-ray is another way to do this. So these little red dots are very interesting. They've had a lot of attention. But I just want to concentrate on one of the things that I've found strangest when we first discovered these. The thing that's very strange to me is that they have intrinsic absorption in the Balmer lines themselves. So I find the colors fine. They're interesting, sort of. But as somebody who's observed quasars for many years, this is really odd. And in fact, I didn't believe that these things were quasars at first within our team. So this is actually not a spectrum of a little red dot. This is a spectrum of quasar. It's called an iron 2 low ionization broad absorption line quasar. So it's like a subclass of quasars. And there are only 11 of these things known that exhibit Balmer absorption out of about 1 million quasars in the literature. So there's about 1 per 100,000 quasars exhibit this. And only 2 altogether were at redshift 1. And so this is, here's the Balmer absorption. You see, this is the H alpha emission line. And so I sifted through the literature to find one of these things. And if you look at their spectrum in the rest of UV, it's bizarre, right? So this is a magnesium-2 narrow line, and then it's basically completely absorbed by metal lines and things in front of that. So from a quasar observer who looks at the intergalactic medium, whenever I see one of these, I throw it out of my sample because it's a weirdo. And some people like weirdos, but I'm not really into those. So then if you look at the so this is that same montage of little red dots that I showed before. And the green ones here are ones that exhibit some evidence for possible Balmer absorption in them. So sort of like 20 or 30% of these things show this thing that, when we first looked at these and everybody said, oh, there's Balmer absorption. I was like, no, you're used to seeing Lyman alpha absorption. This is H alpha and H beta. Those are not the same thing, right? Because in order to get this, when I see Balmer absorption like this, I'm thinking the atmosphere of an A star, not an AGN. So I thought, well, when I see something like that, that's not absorption. What you're seeing is just 2 components of something that are orbiting each other dynamically. And they were like, fine, but we'll just publish it anyway. But the more data that's been taken, I think I'm getting convinced. And so this is actually a much higher signal to noise spectrum of one of these things. And just look at this emission line. This is taken at higher spectral resolution and higher signal to noise. And this looks like a broad emission line that's got an absorber in it. And in fact, this was taken with the IFU, and you can look at the morphology of this, and you see that the morphology of the broad lines is very compact. And then there's other sorts of morphology that are more extended. And so I think that these things really are quite likely to be some sort of AGN, but they have much redder colors, and they're much more common. You see one of these per field, roughly, when you point JWST in a direction, which is very different from these high redshift quasars. So let me talk about one last one that's kind of interesting. So as I've always said, these things show on the blue side evidence that there's a stellar population, but we found one of these things at redshift 7.7 that has no stellar population. And we're wondering what it is, so we might as well talk about it here. We think maybe it's some sort of different kind of object. So here it is. So you see that there's no detection in any of the optical bands until you get to 3 microns and redder. Then it starts to pick up. And what you see here is essentially 0 flux through here. And then this is where the Balmer break would exist at redshift 7.7. And so this would be roughly 3,900 angstroms. And then it comes up like this. And then you see an H beta emission line. We don't have any data to the red of it. But basically it looks like just the red side of a little red dot with no stars. And so just to give you a sense, if you wanted to make this from a stellar population that consists entirely of A stars, the maximum Balmer break you could get in size is about a factor of 3 flux ratio from one side to the other. And this thing is more like a factor of 7. So it's not producible by any known stellar population. And it's also the case that the H beta profile has all kinds of weird structure to it. Doesn't look like a normal thing. And so we've tried to simulate this a little bit, and it turns out you can actually do this. I should mention that there's another object that was found in Jades that looks a little bit like this too, at redshift 7, that just came out. It's a little bit less extreme than this one, but I think there's a few of these out here. And you can actually produce that spectral energy distribution if you put a power law continuum, and then you surround it by a really thick ball of gas that has a lot of convective or turbulent broadening. And then you put 10 to the 24 centimeters of hydrogen in front of it. You can actually irradiate it from the backside, and you generate that Balmer emission line. And then in front of it, there's what is like a stellar atmosphere that produces all the Balmer absorption. It's one model that kind of works, but it's a different way of thinking about this, in that it looks and feels a little bit like a star, except that instead of nuclear fusion, it's producing the energy source in the middle. That it might be an accretion disk with a power law SED that's basically pumping radiation in from the backside. Whether it works or not, we don't know, but it's kind of an interesting thing. And I should mention Rohan Naidu is really kind of leading the work on this. He's the one that found this in one of the surveys. So there's some questions I have about this. So where in the slab is the absorption coming from? Is this dynamically stable, or will it blow apart? The other thing too is it seems like there's evidence that a lot of these things may be obscured in different ways. And so I wonder if, how do you actually, I realized everybody assumes this AGN torus that we are used to just exists, but I don't actually know that much about how it's assembled. But there maybe that literature is out there and I don't know it, but and that's certainly possible, but these are interesting questions. So let me stop there. So it just summarize what I've said, and then I'm happy to take questions after. So we're 2.5 years into JWST operations. I should mention, originally this is half the mission, right? It's supposed to only last 5 years. So we're halfway there. Thankfully, the mission is going to last longer because of the successful launch. But we should just remember, it's not going to be haymaking day forever, but we're making a lot of progress. So here's the things that I feel like have influenced my thinking about early black holes. So first of all, I think the support is stronger that there's fast and super Eddington buildup, and that these black holes really are 10⁹ solar masses within the first gigayear, or at least that they're broad enough, they're massive enough to make really broad H-beta lines. There's tentative evidence that black holes initially grew faster than their stellar populations, and that they might have of order 10% of the stellar mass in some of these cases. I say tentative because I worry about these selection effects for how these early samples were produced. But it's certainly interesting. There's certainly some that seem to be overmassive, but whether that turns out to be the entire population remains to be seen. But to the extent that black holes and their constituent galaxies grow together in some sort of equilibrium, it's easy to imagine that at some point you might predate that equilibrium. Large black holes, the biggest ones, are often, but not always, found in quite biased structures, roughly the mass of today's Milky Way, which means they're rare, but not ultra rare. And that, but quasars, UV bright quasars, are ultra rare. And so if these two statements are both correct, then it has to be the case that the quasar phase might only be 1% of meaning the phase that they're UV bright is only 1% of the total population, which means we got to go and find those obscured ones or the smaller mass ones. There's tentative evidence that the UV radiation is episodic. It turns on and off frequently, and if you have to wait 10,000 years, which is not very long, before it sort of looks like a long-lived quasar. And there's also very tentative evidence that the radiation is non-isotropic. And that there's at least one candidate for this obscured growth, which are these little red dots. I don't think that the number density of those is, I'm not confident enough in the number density to say for sure that these are the ones. So that would close your argument if you found enough of these things to explain the rest of those. My sense is that it will get us partway there, maybe a significant way there, but probably not all. But that's I would not place high confidence on that statement yet, personally. But the thing I would point out about these that I hope people, if you didn't appreciate it before, maybe you would after today, that this Balmer absorption requires very extraordinary hydrogen column densities, and you have to excite this into the second state. So it's similar to these low ionization broad absorption line quasars, which are a tiny fraction of all AGN, but they're a large fraction possibly of these little red dots, which means something unusual is happening in these. Oh, no, there's this last one. There is the unusual objects that resemble little red dots, but there's no stellar pop. So maybe these things are something different, but I think it's too early to say. But just in the interest of speculation and sharing what we know and what we found, I wanted to talk about it today. So that's all I have. Thanks so much.
So I think we should maybe do 1 or 2 questions, just because we're a little over.
Yeah, sorry.
No, they're very exciting stuff. So I guess first from the crowd, and then we'll look at Zoom. Go.
One from early part of your talk. You showed a diagram in which you had a black hole estimate from H-beta and magnesium,
Yes.
right? And you showed all the new points, and they were all lying along that diagonal more or less.
This one.
Yeah. At various times, I've heard people poo-pooing the magnesium line, saying it's unreliable. But I look at this and it looks like it's agreeing perfectly with H-beta.
Yep.
It's a very good diagnostic then.
I think so. Yeah.
Okay. So,
At least we found no evidence to the contrary.
right. And yet there are people who say, if it's not H-beta, I don't believe it.
Mhm.
Magnesium is very flaky.
Yep.
It's not flaky.
I agree. But I thought, we had to do the test with JWST.
You had to do it,
So
yeah,
I
right.
put that as number one and said, for some people, it's not earth shattering. Maybe for you it was.
No, I'm a theorist, I'm just taking people's word.
Yeah.
They say, don't believe magnesium.
Yeah,
True.
yeah,
Yeah, and now, after this, I'll say, yeah, it's as good as it.
yeah. I think it's solid.
Thank you.
One more question, go ahead.
Yeah, in the first point of your conclusion, if you can go back to the summary slide. You mentioned this is what strengthens support for maybe super Eddington buildup. So we believe that these things exist, and they're heavy very early. I guess conversely, you can also say it could be evidence for heavy seeds that are growing
Yes,
Eddington.
yeah,
So I
that's
guess
fair,
what
yeah.
would your opinion be on the super Eddington is more reasonable than having heavy seeds or vice versa?
So, I think it's probably both and, not one or the other. And the reason for that goes back to a comment I made on this slide here. So if you have a heavy seed accreting at Eddington, but maybe it's accreting at Eddington, but is highly obscured. But there seems to be a fair amount of, but I wouldn't discount the possibility that the accretion is very episodic. So what we don't know is whether it's growing all the time and is obscured, or whether it is turning on and off. But if you lessen the amount of time that's available so that it's significantly shorter than the Hubble time, then I think even a heavy seed by itself may still require some super Eddington. But I think there are others in this room who are way more qualified than I am to assess that, but just my intuition. But as I said, I observed the CGM. This is all, I've got most of this by osmosis and collaboration more so than looking at.
Just add a comment that this is quite late in the universe to really say anything conclusive about seeding, so I would go
Yeah.
with Rob saying it would be, but yeah.
I see. Okay. Thanks.
It's the highest redshift guys that are giving us the constraints. on
Yeah,
seeding.
I think that's probably right.
Well, you have a question?
Oh, yeah. You mentioned you need extraordinary NH for these absorption lines. Is that consistent with the amount of NH you need to obscure the X-rays?
I don't know that yet.
Okay.
Is a simple answer. Yes. Yeah, I think we have created cloudy models that will produce that.
Okay.
But
10 to the 24 is kind of
Don't
that's
think that-
it's when it's Compton 6, so.
Yeah. Should do it.
so I think
It is in the
it's
right
like,
ballpark.
it's interesting if it's like in the right ballpark, but
Yeah.
like kind of, right at the threshold of where you might or might not be able to.
Yeah. But I mean, the X-ray background models have a lot of room, a lot of obscure sources.
Yep,
right?
yeah,
So-
I think that's right. So as I said, I think the answer to this question is going to ultimately rest on getting really deep X-ray observations. And that's probably the path forward, but I think JWST will tell us quite a bit more, but I actually have a feeling we're not going to be able to answer that question conclusively. And the existing X-ray telescopes are not up to the job. You can stack lots of things, and people have tried to do that. And that's useful, but they're always just like the stack limits are just a little weaker than you'd like them to be. So.
Anything burning on Zoom? Okay, in that case, I think we should break for lunch. So let's thank you. Lovely.